So, now we are going to discuss friction spinning and drape 2 friction spinning. Friction spinning was originally developed by Dr. Ernst Ferrer of Austria. The uniqueness of the system is that creation of a very large friction field using 2 drums for twist insertion into an assembly of fibers. That is the uniqueness of the system. There could be 2 types of friction spinning machines or friction spinning technology, drape 2 and drape 3. Drape 2 works on the principle of open end spinning, and drape 3 is basically on the principle of wrap spinning. Our focus today will be mostly on drape 2 machine. In both the systems, additionally a filament yarn can be incorporated to produce composite yarns. That sort of flexibility exists, that we can always add an additional yarn, and this yarn, preferably it is a filament, could be either a filament with rigid core, which could be mono or multifilament. It could be an elastic core material, or it could be water soluble filament. So, all types of filaments can be incorporated at the center of the yarn, and that can be covered by another fiber, and we will be able to produce composite yarns. So, this is also possible, and this is possible on both drape 2 and drape 3 technologies. Basic principle, now a diagram you see on the right hand side. Now, fibers from a sliver or from a group of slivers are thoroughly separated from each other by some means, mostly with the help of opening rollers, and these separated fibers are then released in an air stream that carries them to a moving perforated surface, like it is shown here. This is the perforated surface which is moving on the right hand side, and the fiber stream is here. So, we generate a stream of fibers, and the stream of fibers will be landing on a perforated surface. Fibers are then separated from the moving stream by this suction, which is active below the perforated surface. So, therefore, this region there is a suction acting. So, whereas the fibers are landing on the perforated surface, the air is sucked out and the fibers rest on the perforated surface, which acts like a screen. So, there are a lot of perforations are there, and the air is sucked, the fibers remain on the surface. As a result of this, a layer of fiber will form on the perforated surface, and now the surface is not stationary, but it is moving from left to right. So, all the accumulated fibers or the layer of fibers which are there will be brought close to a twisting roller as shown here. The twisting roller is closely spaced with respect to the perforated surface. So, the perforated surface and the twisting rollers are very close to each other. The space is very narrow. It is so narrow that these accumulated fibers cannot really pass through this gap. So, this is the gap which is here, but this gap is very narrow and the fibers cannot pass through. So, accumulated fibers will be coming and it will come into contact with the twisting roll and will gather there. Now, what is going to happen? The accumulated fibers will be rolled now, because this, as it is shown here, this region, if we look at this, if this is the accumulated fibers, like fibers are accumulating here, and then this surface is trying to move this way, and the roller surface is also giving a friction, it is going this way, and therefore, this bunch of material which is here is receiving a torque, and as a result of this torque, this is going to rotate and therefore, it will get twisted. So, the movement of the perforated disc and the movement of the twisting roller. So, this is the twisting roller. These two are actually twisting the accumulated fibers. So, the bunch of fibers, as soon as they arrive over there, they get converted into a twisted bundle of fibers, and then we remove this bundle of fibers, twisted bundle of fiber, which we call yarn, and then we try to wind the yarn on a package. So, this is the principle, that is, we have to have a bunch of slivers, separate the fibers from each other and then carry them forward by a stream of air, allow them to settle on a perforated disc through which the suction is acting. So, the fibers will remain there and the air will move out. The perforated disc will carry the fibers forward, where strategically a twisting roller is placed, and the gap between the perforated surface and the twisting roller is so narrow that the fibers cannot really not be able to pass through, because the fibers has already it has a thickness now. The movement of the perforated surface is quite slow, so that the fiber arrival speed is much more than the fiber movement from left to right. So, fibers will come and many fibers will come and settle on the perforated surface. It will form a thick layer, and therefore, layer is so thick that you will not be able to pass through that narrow gap, and as soon as they arrive near that narrow gap, it receives a torque, and as a result of this it gets twisted. So, that is the principle of friction spinning. Now, because of this principle, what are the advantages we get? Only yarn end is rotated and not the full package for twist insertion. That is the first point. That is, if I want to insert twist, we are only rotating the yarn end, not the package that we rotate in the case of ring spinning to insert twist. And the yarn diameter being much less than the twisting roller diameter, the twisting rate is very high. Ultimately, the twisting roller diameter and the yarn diameter, these two are actually will decide the speed of the yarn end. It is diameter ratio that will matter and therefore, since the ratio is quite big, therefore, for every revolution of the your twisting roller, we get many more revolutions of the yarn, because yarn diameter is much smaller in comparison to the diameter of the twisting roller. Speed of the working elements are very low, resulting less wear and tear, because the twisting roller, if you see, we will see the speed of this, they are much less in comparison to the speed of spindle or the speed of the rotor in the case of rotor spinning or ring spinning spindle. Comparison to both of them, the speeds of the twisting element in this case, which is we will see that there is a twisting roller, is much less. So, wear and tear also will be much less. Low axial tension at the yarn formation point due to absence of yarn balloon. There is no ring traveler combinations. So, tension is very low, and therefore, we would expect very less number of end breakages during spinning, and possibility of dust extraction at the spinning zone is possible, because there are perforations on which fibers are coming and depositing. Through those perforations, we can suck out the dust along with the air also. So, that possibility exists. The other important point is delivery speed is independent of yarn fineness. This is very interesting in this case. Delivery speed is independent of yarn fineness. We will discuss more about it. With change in yarn fineness, the yarn rotational speed will also increase for the same circumferential speed of the twisting roller. Because the yarn tail is receiving motion from the twisting roller through frictional contact. Therefore, if the yarn diameter reduces when you try to make a finer yarn, then the speed of the yarn also will goes up, and therefore, we can say twist will also goes up. So, that advantage, you need not to adjust the speed of the twisting roll. It will automatically, speed of the twisting roll will not change, but speed of the yarn tail, which is actually rotated, and therefore, the yarn receive twist, that speed will automatically increase. But disadvantages are poor fiber orientations, because separated fibers have to slow down or decelerate when landing on the perforated surface, resulting in deformed shapes. This is something which is quite dangerous, because most of the fibers will change their straightened configurations. They come at a high speed and then they slow down, they are made to fall on a slower moving surface. So, they deform because of decelerations, and hence the yarn becomes very weak, because most of the fibers are highly deformed. So, utilization of the length of the fiber is not fully realized. That is one of the serious drawback with this technology. Now, that is the basic principle. Now, we will be focusing more on drape 2. A picture of drape 2 is shown on the right hand side. What we see here, this is the sliver feed, that is, we are feeding a sliver. There has to be some kind of feed arrangement. Then there is opening roller, and then the opening roller is separating the fibers from the sliver and making a stream of fibers. Now, from the opening roller surface, the fibers have to be removed, and for that we have an air entry. Through this, air is blown, and that air is actually going to act on the surface of the opening roller and remove the fibers from the surface of the opening roller teeth. And once the fibers are removed from the teeth, that means the opening roller surface is completely stripped off. The fibers are going to land on friction drums, which are here, drum 1 and drum 2. There are 2 drums on which they will land. So, fibers are fed by feed rollers. They are slightly drafted and then presented to a high speed opening roller. Opening roller completely separates the fibers from the sliver because of their high speed. So, the draft between opening roller and the sliver feed arrangement is very high. As a result, the fibers are thoroughly separated from each other. The air is blown over to remove the fibers, and they are made to land on the friction drum. Friction drum are connected to suction, air suction. You see this side and this side also. This is also connected to air suction. So, the fibers are landing near the nip area of the friction drums. The drums rotate in the same direction. If they rotate in the same direction, then at the nip point, if you look at the direction of of the 2 surfaces, then you will find that they are opposing each other, as if, let us say, suppose this drum is rotating in a clockwise direction, the other drum is also, drum 2 is also rotating in the clockwise directions. But at the nip point, at the nip area, if this drum is going this way, this drum is going these directions. The direction of rotation is exactly same, both are clockwise, but here at the nip area, the 2 surfaces are moving opposite to each other. This is what is going to help us. This is going to actually create friction field. We will see that the cylinders have these drums, they have cylindrical coaxial inserts. This is the inserts. With a slit positioned near the nip of the friction drum. The slit is here. Here is the slit. The inserts are internally connected to a suction pump, like this is connected, this side also is connected. The separated fibers land on the ingoing drum surface and immediately taken towards the nip point. So, we allow the fibers to land, like if this is the surface, the drums are basically perforated, but internally most of the perforations are blocked by some suction inserts, and we draw the air, but the air is drawn from the nip area only. Rest of the air cannot really enter. So, if this is the suction is acting here, the air is entering in these regions near the nip area. There is no air entry from here or here, they cannot enter because these holes are blocked. There is no chance of air to enter from here or from here or from here. only near the nape area the air can enter, and there rest the fibers. So, fibers are there, the air is trying to enter, and therefore, these accumulated fibers will be under some pressure. The oppositely rotating surfaces of the friction drums at the nape point will basically twist the accumulated fibers. Usually, one drum rotate little faster than the other. Between the two drums, this is one drum, this is another. This is drum 1, this is drum 2. One of them will rotate little faster than the other. We will see why it has been done later on. They are practically same, but one is little more, maybe 5% or 10% more than the other. This is going to help to make the yarn little stronger. Suctions through the drums. Suction through the drums help in removal of the dust particles which are still left in the sliver. The yarn is withdrawn by a pair of withdrawal rollers at a speed of 100 to 300 meters per minute. So, once the fibers are at this nape point, they are accumulating there because they are coming at a much faster rate, but their removal rate is slower, and therefore, there is always an accumulations. An accumulation that is equal to whatever count of yarn we expect. And they are receiving twist because of the two drums which are there, and you will see that when we will discuss the twisting actions in little detail. So, once the yarn is formed here, it is withdrawn by a pair of rollers, and once it is withdrawn, it goes to the winding drum for winding in the form of a cone or cheese. Both are possible. So, if you look at the operations which are there in drape to spinning, sliver feed, fiber separations, accumulation of separated fibers, yarn formations and packaging. So, sliver feed is simple sliver feeding arrangements. The feed system will consist of two pair of rollers and can accommodate heavy slivers of 25 to 30 gram per meter, that is 30 almost 30 kilotex for drape 2. Since production is very high, heavy slivers at a slow rate is fed. Slow feeding rate ensures better separation of opening of fibers from sliver. If I feed the sliver slowly and then they are acted by very high speed opening roller, then the separation of fibers is going to be much better. Therefore, we feed heavy slivers. So, multiple sliver feed also improves evenness as well. For mass balance, input weight fed per minute will be equal to output weight delivered per minute. So, whatever I am feeding, same has to be the output. Therefore, N m V 0 is going to be C y into V 1. What is C y into V 1? When N is the number of sliver fed, M is the count of individual sliver in tex, and C y is the count of yarn also in tex, and V 0 and V 1 are the speed of the feed roller and V 1 is the speed of the withdrawal roller. So, V 0 is the speed of the feed roller and V 1 is the speed of the withdrawal roller. So, C 1 V 1 that becomes the yarn delivery per minute in terms of gram per meter or in terms of not meter, gram per minute, and this side loss will be the amount of saliva fed per minute, that is gram per minute. So, these two must balance always, and if it is so, we can find out the value of n, how many salivas I have to fed for producing a certain count at a certain speed, a certain count which is C y at a certain velocity, a certain delivery rate which is V 1, and if I know my daily feed rate is V 0 and if m is the saliva gram per meter, that is the kilotex value of the saliva, individual salivas, then how many salivas I have to feed in the system, we can easily find it out. So, that is a very simple straightforward type of relationship. Like an example, how many salivas of 15 kilotex are to be fed for producing a yarn of 200 tex at 150 meters per minute. The feed rate is 1.0 meters per minute. We have to think of feeding very slow always. So, 1 meters per minute is a slow feed rate. So, if I use that equations, mass balance equations, from there we write n equal to this. In this case, the value of m, value of C y, value of V 1, value of V 0, they are all given, and we can find out n to be 2. Then we need to feed 2 salivas of 15 kilotex. If the salivas are not 15 kilotex, typically cotton salivas cannot be 15 kilotex, it could be 5 kilotex or 5.5 kilotex, something like this. In that case, 15 you will replace by maybe 5 or maybe 6, and we can find out how many n should value will be there, but n has to be always an integer. That we have to remember, that n value has to come in integer. So, some we have to match, n cannot be 2.5 or 2.4 or some 3.2, something like this is not possible. Or keeping n fixed, I can find out what should be the input saliva linear density in kilotex. Now, when it comes to fiber separations, fibers from salivas is separated by rapidly rotating teeth of this opening roller. Opening roller runs at a very high speed, maybe at the speed of 10-12,000 rpm. So, surface speed is very high, and therefore, fibers will be separated from each other from the saliva. The separated fibers are now released into an air stream, and air is blown on the surface of the opening roller by stripping the fiber. So, this is a blower is here. This blower is actually blowing air, and the velocity of the air at this point must be more than the velocity of the opening roller surface. Then only the air will be able to remove the fibers from the surface of the opening roller, and then these fibers will be approaching the friction drum, because they are now going to actually get deposited on the surface of one of the drum or almost close to the nip line. In the fiber collections, the fibers land on the surface of the relatively slow moving friction drum. See, friction drum in this case is a very, they both are perforated and their rotational speed is relatively less in comparison to the incoming speed of the fibers, because fibers are coming in the form of a very thin stream of fibers are coming. We have to actually allow the fibers to form a bundle, and then this bundle has to be twisted. So, in order to make sure that a layer of fibers gets formed on the surface of the drum speed is slow in comparison to the incoming speed of the fibers. The negative consequence of this is that a fiber is coming at a higher speed and settling on a drum surface which is moving at a slower speed. As a result, the fibers will be buckled. So, that is the situation that exists as of now. The fibers are bound to buckle because they are coming and hitting a slower moving surface. Anyway, after landing there, while they are approaching the drum surface, there are three possibilities A, B and C. A is right angle guidance of fibers on the drum surface. See, here they are basically they are coming straight with respect to the drum axis. It is perpendicular, drum axis is here. With respect to the axis, these fibers in the case of A is coming perpendicularly. In the case of B, it is coming at an angle, like this is the angle, and in the case of C, it is also coming at an angle. There are three different ways of guiding the fibers on the surface of the friction drum. Here it is perpendicular. Now, out of this, what happens? We will try to find out or create a situation so that the buckling effect of the fibers can be minimized. Now, if you go for right angle guidance, fibers have to change their direction of motion by 90 degree. They are coming this way and then suddenly they will be falling on it and they will move in these directions. So, coming this way and then moving in these directions, that means directional change by 90 degree. In forward guidance, that is in the case of B, the theta angle is much less than 90 degree. That means, the fibers directional change is going to be less than 90 degree. And in this case, the third case C, the fibers are coming in these directions and then it has to completely change direction in this way. So, almost 180 degree change in directions in the case of C. So, out of the three different configuration of the feed duct, the duct that is carrying the fibers from the opening roller surface to the drum surface, this space is actually in the form of a duct, and there are three different configuration A, B, C. We have to choose a configuration which will distort the fibers to the minimum extent. Forward and backward guidance can be expected to improve the fiber extent in the yarn, can be expected both forward and this is called in the C is the backward. Because of change in directions, there is a chance that they may be able to straighten out the fibers a bit and therefore, improve the configuration of fibers. Now, this has been depicted also by this diagrams like V y if we consider to be velocity vectors of the yarn withdrawal and V f is the velocity vector of approaching fiber and V r f become the resultant wrapping fiber. And theta is the helix angle of the wrapping fiber with respect to the yarn axis. That is, on the yarn tail, as soon as the fiber arrives, once the fiber arrives and it starts getting wrapped around the yarn end which is resting on the drum surface. Now, when it is trying to getting wrapped, because ultimately fibers after landing on the drum surface, it is immediately receiving a torque, because the two drum surfaces are acting on it and any fiber, all fibers which are coming, they are getting some kind of torque from these two friction drums, and as a result they are trying to get wrapped around the already existing tail of yarn which is already there. So, this wrapping angle theta a, in the case of B it is going to be theta b, in the case of C it is going to be theta c. So, the resultant velocity vector is shown V r f in this case, and in this case. And if you look at the wrapping angle, then under identical condition theta c is greater than theta a than theta b. A lesser angle will mean that the fiber will be distributed over a longer length of the yarn and thus will contribute more towards the strength. So, the fiber is getting wrapped over a longer length of the yarn, that is a better way of wrapping the yarn or following the axis of the yarn than if it is wrapped almost perpendicularly to the yarn axis. That means, if the yarn tail, see instead of getting wrapped this way, if the wrapping angle is this is better than this, that is what he is trying to say. So, if we allow them to land perpendicularly, then we will get such kind of wrappings. That means, the fiber extent will be less, fiber will be wrapped over a smaller length of the yarn, and that will not be, fiber will not be able to contribute fully to the yarn strength. Whereas, if they are inclined with respect to the axis to a certain extent, then that kind of wrapping will be better from the point of view of realization of the yarn strength. Therefore, theta a, theta b is the best, that means, this kind of configuration is the best, followed by theta a and then theta c. Theta c can disturb a lot, because the fibers are going this, coming this way and then taking turn these directions, and therefore, its wrapping angle is going to vary a lot. So, that kind of configuration of the feed duct is not really very helpful. yarn formation, if we come on the drum surface, if you look at the, see, initially we have to feed a seed yarn, and then as soon as the fibers keeps coming and they getting attached to the yarn already existing there, and we are pulling out the yarn. After some time, the original yarn will be taken away, will be left out with a yarn tail which is tapered as shown in the diagram, because fibers are coming like this, fibers are coming over the. So, whenever fibers are coming from here, and then it is ultimately it is going from left to right. So, fibers as from fibers which is from the left hand side, as it starts moving towards the right hand side, it receives more and more fibers on the top of it, and therefore, what happens, that means the yarn will be gradually thicker towards the exit end of the machine. This side is the exit. Here, whatever fibers are there, it is coming and falling, they are always less in number. When this goes from this segment goes to the next segment on the right hand side, it receives some more additional fibers. Then that segment is going also moving towards the right, it receives still more fibers. So, as these segments, if we imagine that this tail is actually, if I divide it into a number of segments, and if we imagine that the segment which is at the extreme left, it will keep on receiving fibers as it going from left to right. So, by the time they are reaching the exit end, they will be very, very thick, and the part which is in the extreme left will be thinner. So, at any point of time, the yarn tail will look tapered. Now, the neap area of the two friction drum is the yarn formation zone. So, this is the neap area. So, yarn formation zone is, this is the place, this is the yarn formation zone. Initially, all yarn end is initially and yarn end is introduced. That means, a fresh yarn is always first introduced. The end is sucked and gets attached to the surface of the perforated drum due to internal suction. The moment I insert a yarn end, it will be immediately sucked, and the yarn end tail is going to ultimately settle where? It will settle at the neap area, because that is the area which is through that area or perforations of that area, the air is actually going inside. So, the yarn end also will ultimately settle there. The individualized fibers are continuously released on one of the drum surface that moves towards the neap area. So, any fiber which are getting released from the opening roller surface will also reach that area. The fiber arrival speed is greater than fiber removal speed. So, fiber will start accumulating in the neap zone. The accumulated fibers will be subjected to a torque field created by the surfaces of the two drums. The normal force is due to the pneumatic force. The pneumatic force which will be acting on, if this is the yarn cross section also. So, this is the value of F, which is the pneumatic force which is acting. See, we are trying to suck the air through the perforations, fibers are coming and blocking that air, blocking that perforations. So, a pressure differential will be created. That is what will lead to giving you the force F, that is the pneumatic force. Now, the pneumatic force acting on the yarn which will create the reaction forces R 1 and R 2. So, F which is acting on the yarn cross section can be resolved into two components. R 1 and R 2, and R 1 R 2 are the reaction forces. So, torque created will be by the frictional forces mu R 1 and mu R 2, like mu R 1 is shown here and mu R 2 also shown here. So, torque is going to be mu R 1 plus mu R 2 into dy by 2, where dy is indicating the average yarn diameter, that is the average diameter of the yarn tail actually. See, yarn tail is not uniform, its diameter is not uniform, it is thicker here and thinner in other range. So, tail is not of uniform diameter. So, we go by the average diameter of the yarn tail, and that is d dy dash. So, this is what is going to be the torque, and this torque is going to actually rotate the yarn. Mu is the coefficient of friction between fiber and the drum, and this torque, if we plot distance along the drum and torque, this is the graph we get, that is the torque is almost 0 here, because the diameter of the yarn is almost nil. As the diameter increases, the torque value also goes up, because diameter is more here and minimum here. Assuming the drum and the yarn diameter like capital D and small dy respectively, the rotation of the yarn end for one revolution of the drum is also known as transmission ratio. So, transmission ratio T here is pi capital D by pi dy. So, this d by dy, average diameter of the dy, is known as the transmission ratio. Usually this ratio is to the order of 200, hence one revolution of the drum is expected to rotate the yarn end by 200 times. So, you get a transmission ratio of 200. However, it is difficult to ensure constant contact pressure across the accumulated fibers. Hence, the transfer of motion from drum to yarn end is not 100% efficient, and the yarn end is prone to slip. This end very difficult to ensure that it remains in contact with the drum surface. Now, there are many reasons why it loses contact, and therefore, the transmission of motion from drum to yarn tail, this is a friction drive. Drum is rotating at its own constant speed, tail is resting on it. So, tail is actually friction driven. So, there is a chance of slippage due to many reasons. For better twist transmission, the twisting zone needs to be extended, hence the drums are long. Otherwise, why should we go for long drums? The idea is that if we have a larger surface area of contact from here to there, then transmission of drum speed to the yarn tail speed will be better, slippage will be less. And this is diagram we have already discussed, that friction drums. This is the yarn cross section, mu r 1 and mu r 2 are the two frictional forces resulting into development of torque in the yarn cross sections. That is leading to twisting of the yarn. Now, the count limit in the system. The spinning limit both on the finer and the coarser count side is restricted in comparison to ring spinning. Reason for finer count limits: presence of deformed fibers, low spinning tension and insufficient interlayer migration means as we go towards finer and finer counts, the yarn will be more and more weak, and therefore, spinning will be almost impossible. So, very fine count we cannot therefore, really produce here. Possibility of the yarn tail to pass through the neap aperture of the two drums. That means that if the yarn is too fine through these neap apertures. Next is the possibility of the yarn tail to pass through the neap aperture. See, between the two drums there is a little bit gap we maintain. The drums are not supposed to contact each other, no, they are metallic material, we have to maintain certain distance. If the yarn is too fine, it will pass through this gap. So, very fine count therefore, is not possible, because very fine count yarns will be much less than a millimeter in terms of diameter, and excessive torque for lesser number of fibers in finer yarn count results in instability during spinning. All these reasons we cannot really produce very fine count in this system. And very coarse count: accumulation of too much of fibers in the neap area may cause suction force to be ineffective on those fibers which are away from the suction slot. Consolidation and wrapping of twisting action to be less efficient, and requirement of a greater torque to twist a large mass of accumulated fibers by the friction drums. So, these are the reasons very coarse count we also cannot produce. So, there is a range of count in which the drape to machine can work, but mostly we produce coarse count. Adjustment of twist: the machine twist is the ratio of rotational speed of the yarn end and the delivery rate. So, machine twist is this. Yarn end rotational speed divided by delivery rate. Now, what is the yarn end rotational speed? What is this value? This is going to be the friction drum speed into drum diameter divided by average yarn end diameter. So, machine twist is going to be therefore N d into capital D by average diameter of the yarn and the delivery rate of the machine. This is going to be the machine twist. This is the formula for machine twist. Twist efficiency is the what is the machine twist? What is the actual twist that we get? The actual twist is different from the machine twist due to possibility of slippage, and therefore, twist efficiency is actual twist divided by machine twist into 100. That will give us what is the twist efficiency. Generally, twist efficiency is 15 to 40%. That means so much of slippage is there. The high speed rotation of the friction drum causes high centrifugal force on the yarn end. The end occasionally loses contact with the drum, leading to slippage. The yarn end will jump from the surface of the drum because of the very high centrifugal force which will be acting on them, and therefore, they will lose contact with the drum, and hence slippage will be more. Friction and transmission ratios. These are the we generally talk about friction ratio. Since in the machine the drum diameter is fixed, the ratio of drum speed to yarn delivery speed is known as friction ratio. So, friction ratio is friction drum speed and by delivery rate. So, this is N d by V y, that is called the friction ratio, and the transmission ratio is capital D by dy average, that is the yarn diameter, average yarn diameter. That ratio is called the transmission ratio. The final yarns therefore will be twisted more without any change in twister speed, because the moment the yarn becomes finer, transmission ratio is going to increase, because diameter of the yarn is going to reduce. Thus, twist will get self adjusted. This term, this is very important, without the necessity to change the delivery speed. In this machine, you need not to change the delivery speed to adjust twist, it will be automatically adjusted. One need not to bother about adjusting the twist in this machine. Therefore, the delivery speed is independent of the yarn count. A high transmission ratio also means lower speed of twisting element for a given twist insertion rate, and thus lesser wear and tear of the twisting element. We have already discussed about this, that I need to rotate the drum at a speed of 3000, 2500, 4000 rpm, whereas we we rotate a twister like say a spindle in the case of ring spinning 15, 18,000 rpm or 20,000 rpm. A twister rotor, we run it at 1 lakh rpm or 80,000 rpm, 90,000 rpm. These are very, very high speed of the twisting element. Friction spinning, twisting element is the friction drum. How much is the speed? Close to 3000 revolution per minute. At such a slow speed, the wear and tear is going to be much, much less. So, twist depends upon average yarn diameter, friction ratio, separation between the suction drums, difference between the front and the rear drum speeds. We find that these two speeds are not exactly same. We will discuss about more of them in the coming in some other lectures. Suction air pressure is also another factor which can also decide the level of twist. Specifications of the machine. Fiber, it can handle natural, man-made, recycled fibers and their blends. Staple length 20 to 150 mm, fiber fineness 1.7 to 17 dtex. So, dtex and deniers are very close to each other. Spinning heads 1 to 8 section, with each section having 6 spinning heads. That means, we can have a machine starting from 6 to 48 spinning heads. So many spinning heads are possible. Feed could be cut sliver up to 30 kilotex per head. Bobbin could be cylindrical or conical. Package can be made from weight could be 3 to 10 kg. Yarn delivery speed close to 200 meters per minute. Yarn count 200 tex to 4 kilotex. Use generally coarser count range of yarns we produce. Core, we can put mono multifilament yarns, single, ply yarns, metallic yarns, glass filaments, anything is possible we can put in the core. And the products which are made out of this technology are blankets for automobile blankets, heating blanket, rugs, this is home textiles, upholstery fabric, wall covering, curtains, cleaning rugs and cleaning rags and mops, technical fabric, filter cloth, filter cartridges, heat resistance fabric, protective garments from high tenacity, heat resisting fibers, high tenacity fabric, transport and packaging purpose, carpet and carpet backing. Basically, wherever we can think of a product that needs coarser count yarn, then friction spinning technology may be suitable there. The second thing is that if it requires composite yarns especially, then it will be very, very suitable. So, coarse count yarns and also composite yarns, then this technology is going to be very, very helpful. With this we close today's this particular lecture on friction spinning. This is the we discussed about drape 2 spinning system. Drape 3 is still left. We will discuss about them in the coming lectures, and drape 2 technology is practiced especially for producing technical fabrics, wherever we need very 2-3 different fibers combinations and also coarse count yarns we have to we really need, then this technology will be very, very suitable. Okay, with this we close today's session. Thank you.